Okay, so let's start with the 1-minute papers from last time. And so there's one question, why De Morgan backwards and forwards and the use of them. And I guess, so first of all, the backwards and forwards part, I'm not sure if I understand what you mean correctly, so correct me if I'm wrong. But one point we made last time was that the De Morgan's laws that you might remember from previous classes or from textbooks or whatever. In the logic of Agda, they split up into two directions, and it's not always the case that you get both directions. So in general, you can only go from more information to less information, right? But some De Morgan's laws seemingly in one direction goes from less information to more information, which is not possible in Agda, right? So that's why we have to split them up into backwards and forwards. And as for the use of them, it's very unlikely that you will ever use these De Morgan's laws directly, but you will probably kind of inline the use of them in other things you're doing. And you just, so for example, if you know that you, for some reason, you have not A or B, and you want not of A, then you will take the first part of this and you'll just use that in your other proof, right? Okay. Right, and then there were two pleas for actually showing functions running. So it's a bit of an in-joke for Agda programs that you never run an Agda program. You just type check it and then you're happy. But we'll try to run them when it makes sense. It doesn't, if you think of this as a logic, then you're kind of happy that you just have a function of this type, right? And you don't really care about running it. Whereas sometimes you actually want to get some data out, and then of course it can be interesting to run it. So we'll see if we can remember to run some programs today as well. And then I think there was one more question. Yeah, so the question was, I don't quite get with, which is fair enough. So I thought we'd do one more example of with. So remember, the with was this construct that Agda has that makes it possible to pattern match on some intermediate expression, right? So normally you can only pattern match on things that are on the left-hand side. So here we're pattern matching on if this is an int 1 or an int 2. But sometimes you want to make that case distinction on something which is not immediately one of your arguments to the function, right? And that's where the with comes in. So I thought, as a kind of natural example of this, let's write this little proof, which says that if P of n is decidable for every n, and Q of n is decidable for every n, then P of n times Q of n is decidable. So being decidable is closed on the product, right? So if I can decide P and I can decide Q, then I can decide P and Q. So let's see how we would do this. Okay, so the first thing I'm going to do is I'm going to introduce my assumptions, my arguments. So I know that I can decide P, and I know that I can decide Q, and then I'm given an n, and I have to decide if P of n and Q of n holds for this or not. Right? So if I reload, this a bit bigger. Okay, then we see that I have to decide if P of n and Q of n holds, right? Okay, so I could, now I have a few different things I could do. I could pattern match on the n, but that probably won't help me very much. But I would like to see if, I know that I can decide P because I have this assumption, right? So I would like to see if P is true or not. And that's exactly where I can use with, because if I use dec P of n, and I look at the type of that, then that tells me that P of n is decidable. Right? So this dec P of n is either going to say yes, P is true, or it's going to say no, P is false, right? And that's going to influence if P of n and Q of n is true or not. So if I say with dec P of n, okay, and then I copy everything here on the left-hand side up to the with, put that on the next line, We'll do a vertical bar where the width is, and then introduce one new variable, which I normally call QQ for some reason. It's anything you want here, right? And now if I look at my context, then we see that I have everything else I had before, but I also have one more variable called QQ, which is of type dec P of n, right? So this is that either P of n is true or P of n is false. So now I can pattern match on this variable, and it's going to give me two cases. Either P is true or not P is true. Okay. So if not P is true, then I know that P and Q can also not be true, right? So in this case, I can only commit to say, well, then this is also going to be false. And then I can see what I need to do. Well, I have to give a function which, given the proof of P and the proof of Q, gives me false. So I can do this with lambda proof of P, proof of Q goes to something. Okay, so here I have to give a proof of false, and I have P, which is a proof of P of n, and I have NP, which says that if you give me a proof of P of n, I will give you a proof of falsity, right? So this is NP of P. Okay, but in this case, I know now that P is true, if I'm in this case, but I don't know if Q is true yet or not, right? So I have to do another with on if Q is true. Say with dec Q of n. And then I do the same thing. I copy everything up to the width. Put that, I put a vertical bar, I put in a new variable, and then equals. I reload, and now I have this QQQ in my context, so I can pattern match on that. Okay, so this says that, well, there's two cases. Q can be true or not Q can be true. So in this case, I have P is true and I have Q is true. That means that P and Q should be true, right? So I can say int one of something. And here I have to give a proof of P. Here I have to give a proof. Keep pressing tab. And in this case, I have not Q, so it's kind of the same as in this case, right? I can just copy this, but this time it's not Q that clashes with Q. Right. So the point of the width is to be able to pattern match on something else that's not directly on your left-hand side. So that's the idea. And it's a fun exercise to think what you would do if you didn't have the width, right? If this wasn't a construct. Because you could imagine introducing a helper function that takes one extra argument, right? And then calling that helper function with this expression. And that's exactly what Agda is doing behind the scenes. So the width is it's not necessary in the sense that you can do everything you want to do with a width, you can do without a width. It's just more inconvenient because then you have to make up the name of the helper function and call it and all these things, right? So it's just a bit of nice sugar, yeah. Sorry, when I? So from the bottom, yeah. Third from the bottom, here, yeah. So this, okay, yeah, it's a good question. So the way to read just this line is saying we're defining this function, we have this argument, blah, blah, blah. And then we have two more columns corresponding to the two widths. So we're in the case where this expression turned out to be an ing1 of P. And we're in the case where this expression turned out to be an ing1 of Q. And we're saying in that case, we are going to say ing1 of something as well. And the proof that P and Q holds is exactly the pair P and Q that we got from these two cases. Does that make sense? So that's a disjunction. This is a conjunction. So this is the product, right? I have P of n and I have Q of n. Whereas the way we defined the deck was using the disjunction, which has two choices. You're either an inch 1 or you're an inch 2. So you could try to prove the corresponding thing, right? Saying P is decidable and Q is decidable, then P or Q is decidable, right? But that would be a different proof. Okay. So I hope that gives you some idea how to use the with. So the high-level summary is you want a pattern match on something that's not directly an argument, so you make it an argument with a with, basically. Okay, but let's move on to today's lecture, which is lecture 6. So today we will talk more about equality, because this is another thing that comes up in your coursework eventually, right? And it's one of the hardest things to get your head around, I think, when it comes to using Agda. So just as a little refresher, how is equality defined? And it's defined in the standard library. I think I clicked on the wrong thing. I should have clicked on this. So equality defined as a data constructor with one single constructor REFL, which says that every x is equal to itself. Right? So that means that we can prove x equals x whenever x really is the same as x, or computes to the same thing. So let's introduce addition again as a kind of example. So remember that addition was defined by pattern matching on the first argument. So 0 plus n is n, suc m plus n is suc m plus n. And then what do we have to give in order to show that 2 plus 3 equals 5? So seemingly these are not the same thing, right? Because there's 3 symbols here on the left and there's 1 symbol here on the right. And REFL only applied when we had exactly the same thing, right? But this is up to computation. So 2 plus 3, if I plug that into this definition, well, then 2 is suc of 1. So this is going to be suc of 1 plus 3. And 1 is suc of 0. So that's going to be suc of 0 plus 3. And 0 plus 3 is 3, right? So that's suc of 3, which is 5. So if we look at what the goal actually is here, then we see that it just computes down to 5 equals 5. Right? So REFL is a perfectly good proof of that. So that's fine when you have concrete numbers, then things compute, and it's often quite easy. I mean, it's either basically REFL is going to work or nothing is going to work, right? Because if I change this to 6, well, then REFL doesn't work. And I really have no constructor which says that 5 equals 6, right? Because they are different things. So for concrete numbers, it's REFL or nothing, basically. Okay, but once you throw variables into the game, then things get a little bit trickier. So sometimes it works, sometimes it doesn't, seemingly. So what's going to happen here? Well, we could just skip ahead and see what we need to prove. And we see that the goal is that a whole bunch of sucs of m is equal to a whole bunch of sucs of m's. Right? So REFL, I think, is going to work here as well. Yes. And why is that? It's because both of these are going to compute as much as they can, which if we look at this one first, because plus here was defined by looking at the first argument, and 5 was still something concrete, right? So we're going to hit this case 5 times, I guess, and then we're going to hit this case. Well, we're never going to hit this case. Sorry, we are going to hit this case, yes. So we're going to end up with 5 sucks in front of 0 plus m, which is just going to return to m, right? And similarly here, well, it doesn't matter if we first compute this inner thing. That's going to give us 3 sucks in front of m. And then we compute the outer thing. So that's going to give us 2 more sucks in front of that. And all in all, we're going to have 5 sucks in front of m. So we have the same, exactly the same thing on both sides in the end, right? So we were lucky here that we stated this in the kind of the same order as the definition of plus was defined, right? But if we now just do this innocent thing where we change one of these around, then we see that it's not as easy anymore. So we would expect this to be true, right? That 5 plus m is the same as m plus 5. But still, so introduce an m on the left. That. Then we see this is our goal. So the left-hand side still has a concrete number in the position we care about. So that's computed down to 5 sucks and then an m. But the right-hand side does not have a concrete number in the thing we care about here, right? It just has an m. So we don't know which of these two equations apply because we don't know yet if m is going to be 0 or a suck of something, right? It depends on how we instantiate this m. So if we try to give REFL here, then we just get an error that is not obvious that these two things are the same, right? I mean, if I change this to a 6, then my goal is going to look very, very similar, right? I have a bunch of sucks on the left, and I have m plus something on the right. And I don't know yet if these are going to be the same or not for every m, right? And there's no way for a computer to check that, because then you would have to check infinitely many cases, right? So REFL doesn't work here. So the typical thing to do is to ask, why is it stuck, right? We want both of these sides to compute down to something which is obviously the same. Okay, maybe I change this back to 5 before we forget. And we can see that the left-hand side is not really stuck, right? That's, I mean, it's ultimately stuck on the m, but we do have exposed a bunch of constructors here. But the right-hand side is stuck because it wants to pattern match on the m, right? It wants to look at the first argument, and we don't know what that is yet. So it's stuck because of the m. So then what we should do is we should actually pattern match on this m, right? Because by doing that, we're saying, well, there's 2 cases, m is 0 or a successor, and then we can deal with these cases separately, right? And the nice thing now is that these are exactly the cases that we had in the definition of plus. So that means that that right-hand side is going to compute more. And we can see if we can make some progress. So we figured out why it was stuck. We pattern matched on the variable that was responsible, or maybe we had to do a with on a whole expression if it's not just a variable, but this time we were lucky. Okay, and then we can look at what we have to do in these 2 cases. So we look at this case, and we see that now, thankfully, the goal is simple again, right? 5 equals 5, because 5 plus 0 is going to compute to 5. 0 plus 5 is going to compute to 5. Right? So REFL works here. Okay, then we look at this case, and we see that REFL is not going to work, because again, our goal, these 2 things are not obviously the same, right? But we see, and this is also a typical pattern, we see that we have exposed a little bit more of common structure on both sides. So we see that now, when we know that this thing is a suck of something, then we know that both the left-hand side and the right-hand side both start with a suck of something, right? So we know that if this had computed to 0, for example, then we know that we will be in trouble, right? Because SAC can never be equal to 0. So we have that the first SAC agree, so to speak, and then we have this thing that looks a lot like the thing we started with, right? And we have this thing that looks a lot like the right-hand side of the thing we started with. So if we do a recursive call on M, that's telling us that these inner things are actually the same. So we could use some general combinators. I think we saw the Kong, and I think we're going to see it again soon, which says that we can apply equal things to equal things and get equal results. Or there's again a kind of syntactic sugar in Agda, which says that if you have an equation such as this one, then you can rewrite by that equation. So I can say rewrite by this expression. So what Agda then does, it looks at the type of this expression, which is this, and then it's going to replace all occurrences of the left-hand side of this type in the goal with the right-hand side. So we have one such occurrence here, right? So I say rewrite, I say this, I reload the file, I look at the goal again, and we see that that left-hand side has now been replaced by m+5, which was the right-hand side of the recursive call. So now REFL will actually work. So that's sometimes very handy, and sometimes it's a bit brittle when it replaces too many occurrences of m or something like this, right? But when you only wanted to rewrite by one of them, but you had two m+5 in your goal or something like this. So if it works, great. If it doesn't work, then it might be better to again do things by hand by the combinators we'll see now, right? But okay, so this is the typical pattern for when you have an equality. You're probably not so lucky that REFL will just work off the bat, because if it did, you wouldn't even think about it, right? So you'll have to say, why is this equation stuck? And then you pattern match on that thing. And typically you'll have a recursive call in the non-base case, and maybe you need to do some other fixing up, or after the recursive call REFL just works. But okay, so this rewrite also worked very nicely because we wanted to replace the left-hand side with the right-hand side. But sometimes you want to rewrite on something which is the wrong way around. So you have x equals y, but you really need y equals x to rewrite by that, right? Because the rewrite always goes left-hand side, goes to right-hand side. So if we can show that the equality is symmetric, then we could just plug that in the middle and rewrite by that, right? So let's see if we can show that. Okay. So equality is symmetric says that if x equals y, then y equals x. That seems very sensible, right? And how would we prove it? Well, we could ask ourselves, how could x possibly be equal to y by pattern matching on EQ? Right? And then we see, okay, there's one case to consider. It's the case where x was actually equal to y. So that means that we only have to consider the output where y is equal to x, right? So now the goal is x equals x, and we can give REFL. So this is a good example of a proof or a function which it doesn't make much sense to run, right? Because if you give it a concrete input REFL, then you're going to get a concrete output REFL. It can perhaps be useful to run this function, so we could try to do that. I say 5com of 17. Okay, so this is how I usually run functions. I name something test, and then I reload the file, and then I do Control-C, Control-N to normalize an expression, and then I normalize the expression I just wrote, right? I could have written the right-hand side here in my expression buffer, but this way I can easily change it if I want to change it to something else. Okay, so what do you think I'm going to get if I run this function with 17? What's that, I guess? 22. Well, it's going to give me a proof that 5 plus 17 equals 17 plus 5, right? So true, okay, but we're not quite dealing in true or false here, right? We're dealing in evidence that 5 plus 17 is equal to 17 plus 5. So it's going to give me something in this equality data type, right? So it's, right. So the only thing it really can give me is REFL, right? So let's run it and see. Okay, it did give me REFL. And why was that? Well, it's because when I plugged in 17 here, it was in this case, right? Because 17 is a successor. Then it was doing all of these recursive calls. They were all returning REFL eventually, which meant that we could return this right-hand side REFL. So it makes sense to ask the question, what is the answer? But often the answer is not very informative, right? It just told us that 22 equals 22 in the end. Okay, let's also show that equality is transitive. So if x equals y and y equals z, then x equals z. Right. Eq 1, eq 2. Okay. So I have these two assumptions. This is my goal. Any idea what I should do at this point? Pattern match. Okay, that's an excellent idea. And what should I pattern match on? Both. Okay, that seems safe, right? So I'll do eq1 and eq2. Okay, turns out they were REFL. Let's see what do we have to do now. Well, then we have to show that x equals x. Okay, I can do that. Right. So this is what you often do when you have an assumption of an equality. It's often a good idea to just pattern match on it because that simplifies things, right? But actually, in this case, we go back. If you think about it, or if you try it, it's actually enough to just pattern match on one of these, and it doesn't matter which one. If I pattern match on eq2, for example, then that made y the same as z. So then my goal here is x equals y, and I can just return eq1 instead if I wanted, right? Which is a little bit nicer because it doesn't wait for both arguments to be REFL if you call this function, which means that somewhere else you might not have to pattern match so much. But on the other hand, you could just pattern match on everything just in case, right? And not think too much about it. And similarly, if you change this around, you see that this is working as well. Okay. So here's another really useful combinator that you use all the time. So these, again, you can sometimes get away with just pattern matching. And if the input is REFL, then you don't need to use the sim combinator, right? You just immediately use the result of it. And similarly, if you pattern match on both of these, then you don't need the trans combinator. But the Kong here can be really useful. So this says that if you have a function, then it's going to turn equalities between x and y into equalities between f of x and f of y. Right? So everything respects equality. And that's often very useful. So let's see if we can prove this. Oops. Okay, what should we do? Pattern match on EQ? Yeah, that's really the only thing we can do, right? So let's do it. Oh, okay, we have to consider the REFL case. Okay, but in this case, our goal has again become easy, right? It's just f of x equals f of x. So we can again get back REFL. So that's on the one hand, that's of course important in the sense that if equality didn't satisfy this, then it hardly could be called equality, right? If you can have a function that distinguishes between equal things, that would just be chaos. But it also means that there's certain things you can't do, right? So you can't hope to write a function which makes a difference between 3 plus 2 and 5. You can't say that 3 plus 2 was built out using plus, and 5 wasn't built using plus. But you always have to respect the built-in equality, right? But then we can also now do this. In a different way if you want. Okay, so we're going to do the same thing, pattern match on M, 0 case is still easy. But here, rather than using the rewrite, if we want, we can see that the goal is suck of something equals suck of something, right? So a good move in this situation is often to say, okay, let's do Kong of suck. And reload. And then we see that the goal is the same, but we've peeled off one suck on each side. And then we recognize this as exactly the type of the recursive call. So that's how you would do it without using the rewrite. It's sometimes just a bit cleaner because nothing else, you have some hope of actually reading this program, right? You see that, well, it's a Kong of suck, so the goal here must have been suck on both sides. Because with the rewrite, it's a bit magical what the rewrite is doing exactly, right? You have to understand the implementation of Agda to understand it. Okay. So for what follows here, let's just define this application again, which is not really doing anything. So f$x is defined to be f of x. Just so it's a little bit clearer to see what's going on. And you can maybe believe me if I say that you can prove that addition is commutative. So we had m plus 5 equals 5 plus m before, but this, of course, was nothing special about 5 in that argument, right? So I've just postulated that here so we don't have to prove it, but you could prove it. And similarly, that is associative. It says it doesn't matter how you put the brackets if you add 3 things up, right? You could either add the last 2 things and then the first one, or you can add the first two things and then the last one, and you get the same result. Right? So just postulate this so we can get to something disgusting, which is this kind of slightly weird property. So it says that if you do m plus n plus suck of p, then you can move this suck all the way to the front. So say 1 plus p plus, this suck of p all the way to the front. So it's a kind of combination of associativity and commutativity, right? Because we are rebracketing things, and we're also moving the p to the other side, right?
And the m plus n becomes n plus m also.
Right, we also switch the n and the m, yeah. So we've rearranged things and we've rebracketed things. And Guillaume has given us this proof here, which I hope you agree is not really easy to understand, right? So it's doing multiple steps using transitivity, and then along the way, it's using commutativity and associativity, but this associativity was the wrong way around, so it has used symmetry, and here he wanted to use commutativity under an m plus, so he had to use a Kong, and this is often how you write these things, right? So you start here, and this is the goal, and then, okay, the first instinct you have is you start pattern matching, but then you realize, well, you already done a lot of proofs, so maybe we can just string together the old proofs. That would be a bit neater. And then you realize, well, I can make one step by commutativity. So here I have m plus n. here I have n plus m, right? So if I use commutativity, then maybe that gets me a little bit closer. So I say this is going to be transitivity of something and something. And then here, this is going to be whatever this is and so on. So you often write the proof just trying your way with transitivity and so on. But if you do that, then you end up with this unreadable proof in the end, right? Oops, deleted too much. So that's great for when you're exploring something, but it's not so great if you want to show this to anyone else and make them understand what you're doing, right? So instead, there are these combinators in the standard library that can make this look a bit nicer. So we can go back to see what they mean in a second, but we can just look at what the proof looks like this. So it's the same statement, but this time Guillaume has set things up using these equational reasoning combinators. So the way it works is that we list all of the intermediate steps here. Right? So we start, this is our left-hand side, this is our right-hand side, and then we use these combinations to say, how do I get from here to something intermediate? How do I get from here to something intermediate? And I keep doing this until I'm at the end, right? So then in the goals here goes the actual proofs. So we can say, okay, why is this equal to this? Well, we can see that we have m plus on both sides. So we can hope that this is a Kong of m plus something. And then n plus suc of p is suc of p plus n. Well, that's looking like, what was it? It's commuted to, okay, it's a bit hard to see because this thing here is really suc of p plus n, right? So then we see its commutativity.
Yeah, it's easier to see if you look at the steps on the left-hand side because there's no magic there.
Yeah, so we are saying, okay, let's bracket it like, let's only care about these sub-expressions by doing the Kong. And then here we're saying that this is just swapping these two, right? N and suc p. Okay, and then how do we go from here to here? Well, that looks like it's a commutativity again, right? M and suc p plus n. Okay, and how do we go from here to here? Well, it looks, sorry, from here to here. And that looks like a rebracketing, right? So here we have the bracket on the left. Here we have the bracket on the right. Okay, but if you remembered up here, the rebracketing went from right to left. So here we want the symmetry of this one. That's what we saw down here, right? So the combinators here have a special combinator for applying symmetry to the proof, and it has this thing pointing the other way, right? So that's why that works. And then finally, how do we go from here to here? Well, that's just by computation. So REFL will work as a proof, and there's a special combinator for saying these two things are really the same, but just for readability, I want to list them in perhaps two different ways, right? Okay, and then we can line this up again. So I hope you agree that it's easier to read this proof compared to the disgusting proof up here, right? And what are the parts? Well, we start by saying begin. That's how we start the equation of reasoning. And then we say left-hand side equals right-hand side, where the right-hand side could be some intermediate thing. And we put the proof that these two things are equal in the middle. If we want to use symmetry, then we change the order of the way this y is pointing. And if the proof is raffled, then we can just leave it out. And then we end with this QED symbol, right? So the way we normally do these things is you start. I want to do this again. So I start like this. I realize this is not going to work in one step, so I'll try to use this. So then we have the starting point. So we open equational reasoning. We have begin to say this is the beginning of the equation. And then I say something equals something QED. And I line things up like this. So this is a normal backslash equals equals. This is a backslash less than. So a fancy less than, and this is a backslash greater than, right? So I do it like this, and maybe if I'm feeling confident, I'll already replace the left-hand side with my left-hand side, and the right-hand side with my right-hand side, okay? Then I reload to see everything works, and then I copy the line I'm currently working on to the next line, and I modify it however I want to modify it, right? So I want my first step to be this. Do that. And then if I'm not really trusting myself, then maybe I try to fill in this goal to see that this step made sense. And then I keep modifying this onto whatever I want it to be. And sometimes I work from the bottom to the top, works the same way, right? But that way you can, it's like writing the proof on paper in a way, right? Line by line, rather than having to interact with Agda directly. So, of course, you never really get given such a proof with just the left-hand side to fill in, right? Right, and an important thing to point out is that you can click on these combinators, and you see that these are not built into Agda. It's just a normal definition where, okay, it's a bit more complicated than it used to be maybe. So they work in greater generality, but basically what's happening is that these things get translated to uses of transitivity. This thing gets translated to a use of symmetry, and this thing gets translated to a use of REFL, right? So it's just a nice way to package up the proofs we had before with transitivity and symmetry and so on. It's just more readable, right? So there's no magic, there's no special support for this in Agda. It's just a standard definition in the standard library. Which is kind of nice that you don't need that support. The language can do it anyway. And it actually is quite readable, right? Right, so I think that is a good place to stop for today, but does anyone have any questions? Do you have anything you want to say, Guillaume?
No, I think that's good. That's all we wanted to see.
Yeah. So maybe one thing to say is that it's kind of a judgment call when you want to break out these combinators and lay out your proof this way, or when you just want to use maybe a single Kong, or when you actually want to use a rewrite and so on. That there's no hard rules about when one is better than the other. I mean, it's mostly about readability, right? So if your proof really is just one line for each pattern match or something, then there's clearly no point in writing it with a begin and so on, right? Because you just have begin left-hand side, proof right-hand side, QED, which is typed \QED, by the way. Yeah.
Yeah, I guess one thing I wanted to say, and that we see later on in the file, so I guess we'll see tomorrow, is that because it's not a special purpose syntax or anything, you can use all the usual language constructs, right? So you can let bind the proof. If an intermediate step has a bit of a long proof, you could introduce it in a let first and then use it somewhere on the right-hand side. So we do that later on, where the induction hypotheses are first named at the top level, and then they are used in the equational proof. So it's a design pattern we call embedded domain-specific languages, whereby you design a small vocabulary of useful combinators that are targeting a very specific domain. Here, the proofs of equality, and then you can use them to simplify your programs or your proofs. Here it's proofs, but sometimes it's useful to have this kind of language for programs. And that's actually what we will see in the second coursework. We'll have a small embedded domain-specific language to write a particular type of programs.
Yep. Okay, let's stop here for today and see you tomorrow. Hopefully in person, Guillaume.